Hi, y'all. It's Mrs. Blasky. We're going to cover the last topic in Unit 1 today, which is about PES, or photoelectron spectroscopy. So photoelectron spectroscopy is the process that scientists use to measure ionization energy. The data that they obtain from PES tells us about electron configurations, basically. It tells us about how those electrons are organized and how much energy is required to remove each electron in an atom. So this is not necessarily something brand new, but it's using data to help back up all of the other things we know about the structure of the atom. So what happens in PES is, we shoot a beam of energy with high energy at a sample that has enough energy to be able to ionize all of the electrons in an atom. And so all of those electrons then are bounced into an electron collector, and the detector measures how many electrons are being removed from that sample at specific energies. So if they measure the energy of the ray coming in, and then the energy that that electron is leaving, they can figure out how much energy that electron had to absorb to be able to be removed. That data can be translated into a graph, and we get something that looks like this. So what a PES graph tells us is it tells us a relative number of electrons on the y-axis, and it tells us the amount of energy needed to remove those electrons on the x-axis. So now notice something weird specifically about these PES graphs is that along the x-axis, the higher value is actually on the left, and the lower value is on the right. We structure them that way so that the electrons here that have the highest energy needed to remove them are actually the closest to the nucleus, and then they get farther and farther away from the nucleus as we go to the right across the graph. Notice that this peak has a relative number of 2 electrons. This peak has a relative number of 2 electrons. This peak has a relative number of 5 electrons. So what that means is that on average, for every atom, there were 2 electrons that required the same amount of energy to remove. On average, there were 2 electrons that required this amount of energy to remove from every atom, and from every atom, on average, there were 5 electrons that required this much energy to remove. This is a graphical representation of an electron configuration. If it's 2 electrons, and those are the closest to the nucleus requiring the most energy to remove, then this is the 1s orbital. Again, if this is 2 electrons, and it's second closest to the nucleus, second most energy required to remove, then this is the 2s. This one would be 2p. And we can see that in the relative number of electrons also. Notice that there's 2 electrons in that peak, 2 in this, and 5 here. We know that this is a graph of fluorine. We can compare that to the electron configuration of fluorine, and that is true. Electron configuration of fluorine is 1s2, 2s2, 2p5. So we can use the spacing and the relative number of electrons to help us identify the peaks compared to the orbitals that we are filling up. Notice that this peak is the highest energy. Those are going to be the electrons closest to the nucleus. As we change our electron configurations, as we add in or remove electrons from an atom, changing it from fluorine, let's say, to oxygen or to neon, these peaks and the location of these peaks will shift to the left or to the right, depending on how much closer to the nucleus those electrons are, how much more energy is required to remove those electrons based on the atomic structure. So for example, we've got the peaks and the subshells labeled. It says circle the valence electrons on the PES. Well, valence electrons are the outermost electrons in the largest energy level. So that would be the 2s and the 2p. Would the next electron, i.e. the last electron in neon, be to the left, to the right, or on the peak at 168 millijoules per mole? If I add another electron on here, let's think about what we know about Coulombic attractions. If I move this up from fluorine to neon, neon has 1 more proton, but we're in the same energy level. That proton is going to create a larger effective nuclear charge. It's going to be able to pull those electrons closer to the nucleus, increasing that Coulombic attraction, and making it require more energy for those electrons to be removed. So if I was talking about neon, that 1s would get shifted down a little bit. The 2s would get shifted down a little bit, and the 2p would get shifted to a higher energy level. So it's going to require more energy to remove all of those electrons because we now have more effective nuclear charge with that addition of that proton. We will use these PES diagrams to compare a lot of different things. We can talk about how things are going to happen. We can identify them. We can compare the graphs of element to element to see what differences we can prove. But basically all this boils down to is that PES is a visual and data-driven representation of our electron configurations. We'll do some more practice on this. We'll do some explaining in class. If you've got any questions, let me know. Otherwise, I'll see you later.